Hey everyone, this is a video lesson that I'm using in my AP Calculus AV class, and I'm putting online in case it would be helpful to others as well. In this section, we are going to talk about the fundamental theorem of calculus, and I hope you're ready because it's a pretty big deal. Okay, before we keep going, I should say that there is a link to a printable set of guided notes in the description of this video that you can use to follow along with the problems that I go over. All right, let's start with a huge question here. We got to start big for this section. What is the most important computational discovery in the history of mathematics? What is it? Well, according to the authors of our textbook, Finney, Demanowaits, and Kennedy, this section presents the discovery by Newton and Leibniz of the astonishing connection between integration and differentiation. This connection started the mathematical development that fueled the scientific revolution for the next 200 years and is still regarded as the most important computational discovery in the history of mathematics. Okay, I totally messed up that ending, but whatever. You get it. This is pretty big here. That's what we're talking about. We're talking about something that's pretty big. It's called the fundamental theorem of calculus. All right, so here's some really good news. It's a pretty big deal, but if you're one of my students or if you've been following along with all of my section videos, you already know half of it. You know what's called part 2. I don't know. There's always debate about what's considered part 1, what's considered part 2. This is called also the evaluation part. And it is just using the antiderivative to get the answer to a definite integral, right? To find the area under a curve over an interval. If f is continuous on AB and capital F is an antiderivative of lowercase f, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. We already learned this, right, back in the last section, and we've been using it to evaluate integrals. Like example 1. Take a look at example 1. Use part 2 of FTC, the fundamental theorem of calculus, to evaluate the integral from -1 to 3 of x cubed plus 1 dx. Okay, we already know how to do this stuff, right? What do? We get the antiderivative of the integrand. The antiderivative here is 1/4 x to the 4th plus x. We will now evaluate over the interval, and that means sub in the upper limit for the x minus sub in the lower limit for the x. Evaluate that expression, and I'm not going to spend time typing that into the calculator. I trust we can all do that. We should get 24. Okay, so I've been calling it the antiderivative formula for integrals, but really it's part of the fundamental theorem of calculus. All right, so we already know how to do half of the fundamental theorem of calculus. The big question now is, how does part 1 of the fundamental theorem of calculus work? How do we work with part 1? I haven't even showed you what part 1 is yet, but I want to set it up by doing this part of our notes, and then we'll go back and we'll write in what part 1 says, okay? So if we have y equal to the integral from 1 to x of 3t squared dt, what we are looking at here is called an integral defined function. Okay, now for this one, we can simplify it, right? Take a look at this first box. It says simplify y. Well, let's use the other part of the fundamental theorem to do that. We know that the antiderivative of 3t squared is t cubed. And we're going to sub in the upper limit, which will give us x cubed, minus sub in the lower limit, which is just 1, right? 1 cubed, which is 1. So what we really have as our function here is y equals x cubed minus 1. Now let's find the derivative. Let's find dy over dx. Take the derivative of this. Dy over dx is equal to what? Well, it's equal to 3x squared, right? Which, look at this. 3x squared, and here it was 3t squared. And how did we get it to be 3x squared? Well, the upper limit was an x, right? And so there you have it. That's what part 1 of the fundamental theorem of calculus says. Okay, wait a minute. I have the actual theorem somewhere. Here it is. Okay, and then we'll go back and do the other examples. Okay, here's what part 1 says. If f is a continuous function on any interval, then y equal to the integral from a to x of f of t dt has a derivative, and its derivative dy over dx is equal to f of x. Okay, notice that you have an f of x here in your derivative, and in the integral defined function, it was an f of t. Okay, so now let's go to example 2 and let's try these. Find the derivative of the given functions using part 1 of FTC. Okay, dy over dx indicates we are taking a derivative, but we are taking a derivative of an integral. Okay, so again, you could go through all the steps of simplifying this. It would simplify into what, like sine of x, why can't I think right now, plus 1? No, it's just sine of x because, sorry, sine of pi is 0. Okay, but you don't need to do all of that. If you were taking a derivative of an integral, your lower limit here is a constant. Your upper limit is an x. The derivative is just the function that you see right here, but it's a derivative in terms of x, so it is cosine of x. That's it. Take a look at the next one. You have the function y equals the integral from 0 to x of 1 over 1 plus t squared dt. The derivative of that is 1 over 1 plus x squared. Change the t squared to an x squared in your derivative, which is right here. Now, for this one, notice it's a little bit different. We don't just have a plain x, we have an x squared. Now, we could go through all of the steps of showing why this works the way it does, but I'm trying to keep this video short, so I am just going to tell you that this is just an example where if it's not a plain x, you need to apply chain rule, just like you would be whenever you're taking any derivative of a function and the inner function, I should say any derivative of a composition of functions, and the inner function is not just a plain x. Okay, so here we are going to have cosine of x squared, but then multiply that by 2x. The derivative of x squared is 2x. And that's your answer. What's different about part D? Can you see it? The limits of integration are switched from the other ones that we've been looking at. The x is in the lower limit and the 5 is in the upper limit. We can rewrite that, though, using our order of integration rule to have the x in the upper limit and the 5 in the lower limit if we just make it negative. And then again, your derivative is right here. Just make sure you bring along that negative and write it in terms of x. That's it. Okay, finally this last one, because there is no constant, they are both functions of x, we will need to sub each of them in, apply chain rule, and subtract in between, upper minus lower. So your derivative is going to look like this. It will be 1 over 2 plus e to the x squared times 2x, because the derivative of x squared is 2x, minus 1 over 2 plus e to the 2x times 2, because the derivative of 2x is 2. Let's leave that in an unsimplified form. Don't do anything with that, especially don't combine your denominators. They are not the same denominator. This is an e to the x squared. This is an e to the 2x. Okay, so I'm hoping you're thinking that, oh, this is not so bad. You're just taking a derivative of an integral, which, students like to say, well, they cancel each other out. And if you want to think of it like that, you can. But, what you're doing here is you're skipping that step, that, middle step of simplifying and going straight to the derivative because you know it's right there. Okay, so how can FTC be useful? Well, for our purposes right now, we are going to use it at times when we have a derivative and we don't know how to find the antiderivative. Take a look at the next section. We know that if the derivative is cosine, then the original function was sine of x, right? Or sine of x plus c, you could say. Because if you take the derivative of sine of x plus c, you get cosine of x. But what if I tell you that the derivative is tangent? Okay, do you know what the original function is? Well, not yet, you don't. You will eventually learn how to do the antiderivative of tangent in chapter 6, but we're not there yet. So what do we do with something like this? Well, we kind of just say, okay, the original function is going to be the integral of tangent plus c. Okay, that's not exactly it. We need a little bit more information, but let's do that down here in example 3. Find a function y equals f of x with derivative dy over dx equals tangent x that satisfies the condition f of 3 equals 5. Keep in mind that this is an x coordinate, this is a y coordinate. Okay, so what we're going to do is write a y equals function here, and that function has to have a derivative of tangent. You don't know what function that is. Do not say secant squared. The derivative of tangent is secant squared, but we need a function that when we take its derivative, we get tangent. We don't have that. But what we can do is say, let's make it into an integral defined function. Okay. Now, with an integral defined function, our lower limit is a constant, and you can find a good constant to use right here, right? The 3 is an x coordinate. Remember, your limits of integration are an interval on the x-axis, so 3 would be a good starting point, and the upper limit is going to be x. Now, since the upper limit is x, you don't also want to have an x inside of your tangent function, so we're going to use what's called a dummy variable here. You can use any letter you want except x. We typically use t, but really you can use anything. And then we want a d, whatever variable you choose for in here, right here at the end as well. I'll make it a dt. Okay, this is not quite done though until we address the fact that when x is 3, we have to get out of this a y coordinate of 5. Okay, right now, think about this. This says y equals integral from 3 to x. If we put a 3 in here for our x, if we put a 3 right there, y would be equal to 0, right? Integral from 3 to 3 of anything would be 0. How do we make this function give us an output of 5 when we put in a 3? Well, you just put a plus 5 at the end of it. That's it. The integral from 3 to 3 is 0, but 0 plus 5 is 5. So that's how you construct your integral defined function from this given information. And, you could think of it as using this fundamental theorem of calculus part 1 backwards. And it's something that is helpful for us right now as we are trying to find antiderivatives. Okay. All right, so there's one more for you to try. Find the function with the derivative g prime of x equals e to the 3x squared that passes through the point 0, 7. I would recommend that you pause the video now, try to write that out. I will as well, and I will bring you the answer when I'm done. And I'm back. It didn't take too long. Here it is. G of x can be written as an integral defined function. We can construct it as the integral from 0. I'm getting the 0 from right here to x. That upper limit just always needs to be an x of e to the 3t squared dt. That's our derivative inside of the integral, plus 7, and I got the 7 from the y coordinate given in my point here. Okay, everybody, and that's it. That is the fundamental theorem of calculus part 1. You already know the fundamental theorem of calculus part 2. So now you can say that you know something pretty big about calculus, okay? You're pretty well into knowing calculus at this point, which is, I hope, a very exciting thing. Okay, there will be a part 2 to this video where I discuss net area versus total area and its applications, but this is the end of the video lesson on the fundamental theorem. As usual, I hope it was helpful. Bye.